Welcome to the intersection of technology, cybersecurity, and society. Welcome to ITSP Magazine. You're listening to a new episode of Stories from Space podcast, where your host, Matthew Williams, examines the history of human spaceflight, the breakthroughs that revolutionized our understanding of the universe and our place in it, and the brave individuals who work tirelessly to advance the frontiers of our understanding. Knowledge is power, now more than ever.
The authors acknowledge that this podcast was recorded on the traditional, unceded lands of the Lekwungen peoples. Hello, and welcome back to Stories from Space. I'm your host, Matt Williams. And today, and I know I say this often, but it's true, I wanted to get into another topic that is near and dear to my heart. In this case, it has to do with the habitability of red dwarf planet systems. And this has become an immensely significant question in recent years, thanks to the explosion in the number of known or confirmed exoplanets that are now part of the exoplanet census. As of the recording of this episode, 5,811 exoplanets have been confirmed in more than 4,000 solar systems. And so far, only 210 of these have been confirmed to be terrestrial planets, which is to say rocky and comparable in size to Earth. However, a surprising number of these particular planets have been found orbiting red dwarf suns, many of which are located within 50 light-years of Earth. Essentially, virtually all Earth-like planets discovered within a 50 light-year radius have been found orbiting red dwarf suns. And to make matters even more interesting, many of these were found within their star's circumsolar habitable zone, or Goldilocks zone. As we explored in a previous episode, this term refers to the orbit a planet needs to have in order to receive enough solar energy from its parent star to maintain liquid water on its surface. As we also addressed, planets that orbit within the zone are considered potentially habitable by scientists, meaning that they are a good candidate, at least in theory, for supporting life. And to give you a sense of some of these planets, a number of familiar names are likely to leap out here. The potentially habitable planets that are within 50 light-years of Earth include the closest exoplanet to our solar system, Proxima b, which is located in the Proxima Centauri system roughly 4.25 light-years away. And Proxima is part of a trinary star system, which consists of Alpha Centauri A and B, a tightly bound Sun-like star, along with a slightly less massive orange dwarf star, and Proxima Centauri, a more distant red dwarf star. And based on the best estimates we have available, this planet is believed to have an equilibrium temperature of about minus 43 degrees Celsius, or minus 49 degrees Fahrenheit. Now, while this may sound bloody cold, keep in mind that Earth's equilibrium temperature is minus 18.15 degrees Celsius, or minus 0.67 Fahrenheit. So, certainly more frigid on average, but as we shall explore, this is due to the nature of its orbit, which is tidally locked. Second, you have Ross 128b, another rocky planet that's located in Ross 128, roughly 11 light-years from Earth. And according to our estimate, this planet is even balmier than Earth, with an equilibrium temperature of 7 degrees Celsius, or 44 degrees Fahrenheit. And then you have the TRAPPIST-1 system, which possesses no less than 7 rocky planets, located roughly 41 light-years from Earth. Now, 4 of those 7 planets all reside within the star's circumsolar habitable zone. And whereas some are more suitable to life as we know it, they all manage to make the cut. Whereas the innermost planets, B and C, are considered far too hot to retain an atmosphere, planets D and E are both comparable in size to Earth, although less massive, and have equilibrium temperatures of about 15 and minus 46 degrees Celsius, respectively, or 5 and minus 46 degrees Fahrenheit. And while planets F and G are more massive, making them comparable in size and mass to Earth, they have lower equilibrium temperatures. They get quite frigid, minus 73 and minus 91 degrees Celsius, respectively, or minus 100 and minus 132 degrees Fahrenheit. And so, these and other exoplanets that have been found orbiting red dwarfs, they've indicated to scientists that in terms of rocky planet production, red dwarfs are pretty good at turning them out. And not only that, they're pretty good at turning out ones that will orbit within their habitable zones. And when you combine that with the fact that red dwarf stars are the most common type in the universe, accounting for 75% of stars in our galaxy alone, you can begin to understand why the question of whether or not these stars could be habitable is such a big deal. For SETI researchers and those who have dreamt of the day when we might achieve contact with other life in the universe, or just find evidence of it and thus know that we're not alone in the universe, red dwarf stars present a very, very encouraging case for life. Knowing that these star systems could produce rocky planets and habitable planets to boot would exponentially increase the odds of us ever finding extraterrestrial life and extraterrestrial civilization. So naturally, all of these planets are considered excellent opportunities for follow-up studies and also for robotic precursor missions when they become available. Concepts like Breakthrough Starshot or Swarming Proxima Centauri have been proposed. Unfortunately, scientists still aren't sure if life could actually survive on any of these potentially habitable rocky planets that orbit these red dwarf suns. And this is due to a number of very interesting characteristics that red dwarfs have. Compared to our sun, they are low mass, very long-lived, remaining in their main sequence phase for up to trillions of years, and are also dim and rather cool compared to our sun. On top of that, they are prone to flare activity, which, for many scientists, rules out the possibility of life existing there, at least for very long, especially in the event of super flares, which are powerful enough to eliminate an atmosphere as dense as Earth's. Now, given the fact that we have not been able to study any of these planets directly yet, because of their smaller size and because they orbit rather closely to their suns, scientists are forced to infer what conditions could be like based on both known and unknown parameters. And because of this, the debate goes back and forth. Are red dwarf systems habitable? And with every new bit of research that emerges, it seems the pendulum swings one way or the other. And to summarize the challenges that life would face on these worlds, 4 basic categories can be identified. One is flare activity. The second, as mentioned, has to do with tidal locking, or the nature of orbit with these planets around their suns, that they may, in fact, have too much water to be considered habitable, and that they might not be getting enough of the right kind of photons to fuel processes like photosynthesis, which, as we know from studying life on Earth, was absolutely essential to creating life as it is today. So to address tidal locking first, because this is related to several other issues here, when it comes to red dwarf stars being smaller and also cooler than your average sun-like star or anything larger, this means that their habitable zones are narrower and much closer to the star's face. So essentially, any planet that is orbiting within its habitable zone is going to be tightly bound to the star, and its gravity will affect the planet's rotation. And this is something that astronomers have observed for a very long time with Earth's moon. We know from millennia of observations and decades of direct studies there since the space age that when we look up at the moon at night, we are constantly seeing the same side. And what we know as the dark side of the moon is actually not dark, it's merely the side facing away from us. It's merely dark in the sense that it's not well known. In any case, this is due to tidal locking, or otherwise known as synchronous rotation, where a planet's rotation becomes synchronized with its orbit around a larger object, which leads to one side constantly facing towards it. And in the case of a rocky planet orbiting within the habitable zone of a red dwarf sun, this means that one side will experience constant daylight while the other is in perpetual darkness. Alternately, the planet may be slightly farther out, still within the habitable zone, where it may achieve a 3-to-2 orbital resonance, which is precisely what Mercury has with our sun, which means that the planet will experience 3 spins on its axis for every 2 orbital periods it makes around its sun. And as a result of this, you do not have one side with perpetual daylight and the other side with darkness, but rather one side experiencing daylight for an extended period of time. In Mercury's case, it has a rotational period of about 59 days, but an orbital period of 88. In other words, if you add up 3 rotational periods, you end up with 176 days, which is the equivalent to 2 orbital periods. 88 times 2 equals 176. As for what this means for anything on the surface, rather than one side experiencing constant daylight and the other side experiencing constant night, you have a situation where a solar day, as it's called, which is to say the time it takes for the sun to set and rise again and return to the same place in the sky, which on Earth is 24 hours, will also last 176 Earth days. So basically, planets orbiting red dwarf stars are likely to either experience very long days and very long nights, or constant day on only one side of the planet. And this could have significant consequences for habitability. Because if, in fact, a planet receives all of its solar irradiance on one side, it will likely become what scientists refer to as an eyeball planet, which could be either hot or cold. And whereas a hot eyeball planet is likely to be dry and irradiated on the sun-facing side, the dark side is likely to be covered in water, most likely frozen. On the other hand, cold eyeball planets are likely to arise where you have rocky planets with an abundance of liquid water, and on the sun-facing side, you'd have a liquid water ocean, whereas on the dark side, it would be completely covered in glacial ice. Unless, of course, there's adequate heat transfer between one side of the planet and the other. And this has been the subject of considerable research. And what scientists have determined is that the presence of a sufficiently dense atmosphere to protect from solar irradiance on the sun-facing side, plus an adequate supply of water, could, in theory, allow for enough heat to be transferred around the planet for it to be circulated to the point that a habitable environment could be maintained and life would have a fighting chance. This brings us to the issue of flares. As noted, red dwarf stars are known for being more variable and volatile than their larger stellar peers. They can lose up to 40% of their luminosity for months due to sunspots forming across their surfaces, and at other times they can double their brightness by emitting a giant flare or super flare. And according to information gathered by NASA's Galaxy Evolution Explorer, which was a space telescope designed to survey the universe in the ultraviolet, even calmer and older red dwarf stars produce lots of flares. And while the kind of flares a red dwarf would produce are lower in intensity than what is typically observed with more massive stars, they are much more frequent, and they are especially bright in the ultraviolet wavelength. And as we know from research here on Earth, ultraviolet radiation can be harmful to life. In sufficient quantities, it can kill, especially where exposure is persistent or if the intensity of it is high enough. Ergo, rocky planets that are tidally locked with their red dwarf suns will be exposed to rather powerful bursts of radiation that will consistently hit the planet's atmosphere on the same side. And the concern here is that that kind of activity will strip the planet's atmosphere over time, unless, of course, the planet has a magnetic field. And this is what scientists have observed with Mars. It is understood, thanks to multiple lines of research, that Mars once had a magnetic field, but that it disappeared roughly 4 billion years ago, and as a result, the denser atmosphere that was once there, which allowed for liquid water on the surface, it was slowly stripped away, and the surface became dry, irradiated, and very, very cold. So this could be the fate of those tidally locked planets around red dwarfs. But to make matters worse, astronomers have observed super flare events that were 10,000 times more energetic than the average. So while regular flare activity could have a limited effect on a planet's atmosphere and any life on the surface, The superflares that have been observed would be capable of stripping an atmosphere entirely, and rather quickly at that. And to investigate this further, there was a 2020 study by researchers from the University of North Carolina and the University of Barcelona, which attempted to assess the impact of superflares on planetary habitability for rocky planets. And they found that planets orbiting within the habitable zones of a red dwarf sun may experience, quote, life-prohibiting levels of UV radiation, though they did indicate that microbial life might still be able to survive. And another study released in 2024, led by the Cavendish Laboratory at the University of Cambridge and the Institute for Astronomy at the University of Hawaii, and the Center for Cosmology and Astroparticle Physics at Ohio State University, they determined that red dwarf suns emit more radiation in the far ultraviolet part of the spectrum than previously thought. And this is especially worrisome because the far infrared part of the spectrum is where the most deadly rays reside. And in fact, far UV radiation has been used in medical science for destroying viruses, bacteria, and fungi. So when considered alongside the 2020 study that said microbial life could survive, it's beginning to look like it would not. Furthermore, in 2017, researchers from the Harvard-Smithsonian Center for Astrophysics, Professors Lingham and Loeb, conducted 2 studies that attempted to model flare activity, specifically in the TRAPPIST-1 system. In their first study, they considered how the system's planets would experience elevated levels of stellar wind pressure, which would strip their atmospheres over time. In addition, they found that strong flares in the UV and X-ray band would further strip the planet's atmospheres. And in their second study, Professors Lingham and Loeb calculated that TRAPPIST-1 bombards its system of planets with stellar winds that are 1,000 to 100,000 times more powerful than solar wind. And it was also in the study that they determined that the TRAPPIST-1 star's magnetic field is likely connected to its planet's magnetic fields, assuming they have them. And whereas the presence of a magnetic field would ordinarily provide protection against stellar wind, the fact that these planets would be connected that way, this would allow stellar wind to flow directly from the star onto the planet's atmospheres in succession, making it especially detrimental to their atmospheres. And making allowances, though, for sufficiently dense atmospheres and magnetic fields that could prevent atmospheric stripping, another issue with red dwarfs is the wavelengths of light that they emit. And according to current research, most of the photons that red dwarfs emit are in the red and infrared wavelengths, which could mean that any life on the surface would not be getting the right kind of light in order for photosynthetic organisms to emerge and evolve. And according to the fossil record, the emergence of photosynthetic organisms happened here on Earth roughly 3.5 billion years ago, and they altered Earth's atmosphere, which was predominantly composed of nitrogen, carbon dioxide, and volcanic gases, and they began to slowly convert the CO2 into oxygen gas, which led to some drastic changes and to the evolution of more complex organisms. And this was a major evolutionary event because, for the first billion years, simple bacteria were the only life that existed on planet Earth. But from this point forward, known as the Great Oxygenation Event, evolution was essentially accelerated. And essentially, photosynthesis comes down to plants, bacteria, foliage. They absorb light in the red and blue parts of the spectrum and reflect it out as green. But since light emitted by red dwarfs falls within the infrared and red parts of the spectrum, photosynthesis may not be able to occur. In addition, in a bit of a twist, a 2000 study by astronomers at the Harvard-Smithsonian Center for Astrophysics, they considered that while red dwarfs may produce too much UV in the form of superflares for life to emerge and thrive, that they also may not produce enough UV radiation for early life to emerge as part of their regular cycle. And specifically, this study looked at UV radiation and how it may have allowed for early life to emerge because it played a major role in the formation of ribonucleic acid, or RNA. And it was the emergence of RNA on Earth billions of years ago that also allowed for the evolution of complex organisms. And according to the research team, Rocky planets that orbit red dwarfs receive, on average, about 100 to 1,000 times less UV radiation than Earth. And last but not least, research conducted on the many rocky planets that have been observed around red dwarf suns have determined that perhaps they have too much water. In particular, a 2016 study led by researchers from the University of Bern, they modeled the formation of planets around red dwarf stars and concluded that in 9 out of 10 cases, rocky planets would be more than 10% water by mass. And for comparison, Earth, even though we know that the surface is predominantly covered in water, water nevertheless only accounts for 0.05% of the planet's mass. And this was followed by a study in 2018 by the Arizona State's School of Earth and Space Exploration, where they examined the TRAPPIST-1 planets and concluded that they would range from 15 to 50% water by mass. In a similar vein, the Pale Red Dot campaign, which is an international collaboration dedicated to finding rocky planets around red dwarf suns, they conducted a study in 2016 using a series of internal structure models, and they found that super-Earths, rocky planets that are several times the size and mass of Earth, that they too are likely to have many, many times the water of Earth. And another study based on Kepler data combined with the European Space Agency's Gaia Observatory, it indicated that super-Earths that are 2.5 times as large and up to 10 times as massive as Earth are likely to be up to 50% water by mass. And this is rather significant because, according to the current exoplanet census, super-Earths account for roughly 30% of all confirmed candidates. Now, of course, the current exoplanet census is hardly complete, but nevertheless, this does indicate that super-Earths are quite common out there. And what this would mean is essentially most of the planets, at least those that we can currently account for, would essentially be water worlds, which is to say their structure would be that of a rocky and metallic core surrounded by a very thick mantle of water. And this water would likely be frozen on the surface except for the sun-facing side, so once again you have an eyeball planet. But the depth of the water would imply that you'd have a liquid upper portion on top of a extremely dense, under very tight pressure, solid portion. So you'd have a very thick sheet of ice formed up against the core, which is in a solid state, not because of temperature, but because of pressure. And this is much like what scientists predict with the gas giants, that you have hydrogen under such intense pressure that it becomes metallic hydrogen. So all of that is essentially very bad news for life, at least as we know it, because using Earth as our template, research has shown that a careful balance between oceans and continents is essential to the evolution of life. It certainly was for life here on Earth. In fact, the Cambrian explosion, which was a period of rapid evolution of life, which took place around 540 million years ago, this saw most of the major animal phyla that exist today suddenly appear in the fossil record. Now, by suddenly, of course, we mean over the course of many millions of years. But scientists for a long time have struggled to explain how this explosion occurred, and one of the predominant theories is that it had to do with the breakup of the supercontinent Gondwana. And so as this supercontinent broke apart to form smaller continents that began drifting apart, this created a lot of shallow waters and reefs and lots of islands, which gave rise to all kinds of niche environments that over time led to the emergence of many new types of life forms. So with a water planet, where water is covering the entire surface up to a considerable depth, hundreds of kilometers, maybe more, it's not likely that life would have a chance. Evolution would likely be stunted and slowed. Also, as noted, the interior structure of the planet, a major ice sheet between the core and the upper ocean, this too would cause problems because on Earth, and this is also believed to be the case with several icy moons that orbit Jupiter, Saturn, and beyond, the exchange of heat and chemicals, Earth's mantle and its oceans, is believed to have given rise to the very first life forms here on Earth. According to the fossil record, life first emerged on Earth around hydrothermal vents on the ocean floor. And so on a water world, this would also not be able to take place, which would have dire consequences for the emergence and evolution of life as we know it. However, there is some good news to all of this. As I said, the research has gone back and forth, and while many studies conducted indicate that red dwarf planets might actually be able to support life after all, in fact, a 2021 study based on data from NASA's Transiting Exoplanet Survey satellite demonstrated that red dwarfs tend to release their largest megaflares around their poles. So while orbiting planets would not be spared from all of its flare activity, they would be spared from the worst. So those massive flares that could blow off an atmosphere in one shot, not likely to hurt them. In addition, a 2018 study led by researchers from NASA's Goddard Institute for Space Studies showed that planets like Proxima b could be habitable despite the fact that they're tidally locked. And the NASA researchers, they demonstrated this through 3D climate simulations, which showed that a dayside ocean could allow for sufficient heat transfer so that Proxima b wouldn't become an eyeball planet. Third, a NASA-supported study that was released in 2023 showed that regular flare activity, as opposed to super flares, could actually assist in the formation of amino and carboxylic acids, the fundamental building blocks for life. And what this means, essentially, is that while orbiting planets may not get enough UV radiation on average from their red dwarf parent stars, a few flares along the way could provide the needed push so that evolution would not be so much stunted as subject to lulls and sudden accelerations. And last but not least, in 2016, Professor Avi Loeb and colleagues from the Harvard-Smithsonian Center for Astrophysics, they conducted a series of simulations that showed that red dwarf suns may have the edge when it comes to creating life in the long term because they are so very long-lived. Given what we know about the evolutionary history of life here on Earth, it is understood that life does take a long time to get going. As mentioned already, for the first billion years, life on Earth consisted of single-celled bacteria. It was only over time that it began to build up and diversify to a very great extent. And so in this respect, based on numerical simulations, Loeb and his colleagues concluded that habitable planets orbiting red dwarf suns have the best chance over the long haul of producing life. And there's also some ambivalent news in all this. According to some other lines of research, it's possible that planets orbiting red dwarf suns may be transiently habitable, but not inhabited. And this is based on the fact that they may have too much oxygen gas in their atmosphere early on in their evolution in order for basic life forms to emerge. And what this comes down to is red dwarf stars, given that they are extremely long-lived, they also have extended pre-main sequence phases. And what this means is that between the formation period of a red dwarf sun and the point where it enters its main sequence and it's producing enough light and heat in order to be supportive of life and habitability on its orbiting planets, there is a billion-year lull. And during this period, any planets that are orbiting within what will become their habitable zones, they would be exposed to higher than normal levels of radiation. And so if they have water on their surface, it will likely be chemically disassociated to create hydrogen and oxygen gas, and this is known as photolysis. And this is where water, H2O, is essentially broken down into its basic constituents, and whereas the oxygen will bond to create oxygen gas, the hydrogen gas, because of its low atomic weight, would be lost to space. The oxygen gas would be retained, and so red dwarf planets might have oxygen-rich atmospheres, but which are not the result of photosynthesis. Once again, as we know from the fossil record, Earth's environment prior to the Great Oxygenation Event was very, very different. And it was these conditions, where the atmosphere was rich in volcanic gases and carbon dioxide, This is what allowed the first single-celled basic organisms to emerge, which developed photosynthesis and began to convert the atmosphere. Oxygen gas is hostile to such life forms. So by having an oxygen-rich environment early in the planet's history, it is possible that life, at least as we know it, would not emerge at all. To that end, it has been suggested that humanity could seed these planets with basic bacterial organisms, ones that evolved to live in an oxygenated environment, and that this could allow for life to emerge and grow on these planets. And examples of this idea include Dr. Claudius Gross from the Institute for Theoretical Physics at Goethe University in Frankfurt, which he named Project Genesis. And he proposed this in a 2016 paper where he said that robotic missions equipped with gene factories or cryogenic pods could be used to distribute microbial life to these transiently habitable exoplanets as a way of preparing the planet for more complex life, which would evolve with time. So, on balance, the question remains, could these planets be habitable? And at present, all indications point to maybe. Unfortunately, we don't know because we don't yet have the capacity to image these planets directly, which is a major challenge given that they orbit rather dim stars. If we can get a direct picture of these planets, if we can study light reflected off their atmospheres, then we would be able to know what the composition of their atmospheres are and whether or not they have sufficiently dense atmospheres that can, over time, support the emergence of life. And in the long term, robotic precursor missions, ideas like Breakthrough Starshot or Swarming Proxima Centauri, and others that call for light sails or magnetic sails that could fly to these nearby exoplanets and take pictures, gather data, and transmit it back to Earth, all within the space of a few decades. Until we have missions like that, we really can't answer definitively whether or not the most common star in the universe, which seems pretty good at forming rocky planets that would orbit within the star's habitable zone, could actually support life. And in the context of exoplanet research and astrobiology, this is a major unresolved question, in large part because scientists aren't sure if they're casting a wide enough net. Naturally, we're taking the low-hanging fruit approach, which consists of looking for Earth-like planets that orbit Sun-like stars, and also, of course, following the water and looking for biosignatures that include oxygen gas, carbon dioxide, etc. But as I've said before with this podcast, we are now at a time when we're not going to have to wait much longer for the situation to change. Thanks to the James Webb Space Telescope and the next generation telescopes that are planned, such as the Habitable Worlds Observatory, the Nancy Grace Roman Telescope, and the European Space Agency's Plato and Ariel space telescopes, not to mention several ground-based telescopes that will have 30-meter-wide primary mirrors. Astronomers will be able to study these planets, smaller, rocky planets that orbit more closely to their suns, in the not-too-distant future. Direct imaging studies will become a reality, and at that point, the process that we currently see, where we are transitioning from exoplanet discovery to characterization, that is really going to be complete. We won't just be finding new exoplanets and then inferring what conditions could be like on their surface based on orbital parameters and size and mass. We'll be able to look directly at their atmospheres and see what chemical concentrations are there, possibly finding biosignatures and even technosignatures. That will be a very exciting day because if we can in fact confirm that some, if not all, red dwarf stars are capable of having habitable planets orbiting them, it will mean that habitability is ubiquitous throughout the universe, because the most common star in the universe has a relatively good shot, if not 100% shot, at supporting life. Be sure to tune in next time where we will talk about the discoveries of the James Webb Space Telescope so far, and how they have both confirmed and upended many things that we've believed about the universe. In the meantime, thank you for listening. I'm Matt Williams, and this has been Stories from Space.
We hope you enjoyed this episode of Stories from Space podcast with Matthew Williams. If you learned something new and this podcast made you think, then share itspmagazine.com with your friends, family, and colleagues. If you represent a company and wish to associate your brand with our conversations, sponsor one or more of our podcast channels. We hope you will come back for more stories and follow us on our journey. You can always find us at the intersection of technology, cybersecurity, and society.